because it feels like you're just standing on sheet metal.
I've actually flown one of those.
Really?
Yeah,
Yeah.
B-17.
I mean, probably worse than that sheet metal. Yeah, it's pretty. It's still very plain, but it's just like amazing. It's like it's got these turrets on top. It's just got this big
You
cockpit.
should see what it's like when you fly. It makes a lot of noise. There's so much air racing through there. Morning. Yeah, when I flew it, they had this is back in the 90s when they allowed pilots of the pilots to fly. But they had opened up the navigators. There was like a hatch in the roof that they would open up, and you could stick your head out on the airflow. And they had that open, and it literally flooded the entire fuselage with air. It was just like really breezy in there. And then the engines obviously are super loud.
Yeah.
You know, the only time it was quiet was when I was flying the planes.
It's very tight to go into the back, because you can like completely travel along the whole tail and everything.
Yes, yeah.
It's so interesting to be in those.
Oh, it's so very much like
the bomb bay is big. I mean, like they have. I know they had big bombs in there, and it was just really cool. Like it was just amazing to see it. I mean, it's probably one of the few places where they allow you to be in some of the planes, but you have to have somebody there with you. But
yeah, they don't. I know nowadays they really restrict access to those planes. I know if you ever get over to London, there's a couple of air museums over there. There's one on the north side of London. I'll take tour groups there, and I do the Duxford Air Museum, which is north of London, about an hour or so, hour and a half. And that's a huge air museum. It's like our Smithsonian. So if you ever find yourself there, definitely give me a call before you go, because I'll give you a map to all these places. There's some really awesome museums there.
Europeans really like museums, huh?
They do. And actually, all those museums in London are all free.
probably the most interesting point overall, though, is they had I think it's the right president. I always get mixed up, but they had Eisenhower's from Kansas, right?
I think so.
Yeah, they had his plane that he flew actually there, and it was just his price is like a small, like kind of similar to a Cessna size. I don't know exactly what it was, but it was just I mean, he had a pilot's license. He did fly, but then at some point, Secret Service or something found out they're like, you're not allowed to fly. Somebody has to fly for you. But like, it's like he actually flew that plane, and it's just that you can see the presidential like seal or whatever on it, and it's just like I got to sit there.
He actually did fly himself.
Yeah,
really. Wow.
It's just a really cool just thing. Like I got to sit there, and I'm just like, it's a pretty cool plane just to see.
Wow.
And they have so much. They have they got a few military planes that are donated from the military. It's like they'll still be like reactivated if something happens. But
yeah, that's
they have
really
so much. They have probably like
maybe that
Middle America Air Museum. It's an old air. I think it was a factory.
Is that on the
It's in Kansas.
list or whatever?
Maybe, I don't know. It's just an amazing place. If you ever get the chance to be down that area, you have to see it because it's just got so much. I mean,
that's fascinating. Well, I'll have to put it on my list of things to do. So, all right. Let's see. You guys doing, Tegan? Want to go in there? Helen? All right. Well, we're going to dive right in, guys. So we're going to do 2 chapters this week. Both of them are on weather. One is on the theory, and the other is on weather reports, aviation products, basically, weather products for pilots. So, so this is session 12. I think last week we left off on session 11. We were talking about performance charts and stuff like that. Does anybody have any questions on performance charts at all? Jeez.
Oh, I do. On the written test, do they give you like the charts?
They'll give you the charts, yeah. And actually,
like a paper form?
Give you a charts. It's a testing supplement.
Oh,
And it's a
okay.
book. I don't have one with me, but if you go to your SIA account in there's you can download the PDF of the actual supplement that they're going to give you in the test.
Okay.
So you'll actually have it. I would highly recommend all of you get that supplement, that testing supplement, and go through it because you become familiar with it. Because when you take the test, you're going to have the same supplement. They're going to ask you questions out of that supplement. Like they'll have like a sectional chart, or they'll have these performance charts. And if you get familiar ahead of time with what's in that testing supplement, it's going to make that test so much easier for you because you're going to know where to turn to. Plus, you're going to be familiar with what they're talking about when they say, go to this sectional and point out this airport. What is the AWAS frequency for the airport at this? And if you have that ahead of time, you'll do really well. I would print it out if you could.
Okay.
If you can in color, because they do a lot of color coding in there. So, any other questions at all? Weight and balance. You guys remember ARM? Okay, good. Excellent. All right, so let's talk about the atmosphere. So atmosphere is composed of about 21% oxygen, 78% nitrogen. Don't have to worry about that for the test. But that's something that the FAA figures you should probably know. One thing that they will talk to you about is the structure of the atmosphere. So here's the planet Earth. There's the troposphere, stratosphere, mesosphere, and then the thermosphere. Troposphere is anywhere from 20,000 feet to about 50,000 feet, depending on where you are in the world. Like the poles, it's closer to like 20,000 feet. Because that's where it ends. It starts at the surface. The troposphere starts at the surface. And then at the equator, because, we'll look here at the equator, because air has a tendency to flow down toward the center of the Earth. That's where the major gravity is there. It's just going to flow there. It's also going to rise up a lot higher. So the troposphere actually is higher there. So it's from the surface up to about 50,000 feet. Yeah.
So how high would the troposphere be here?
It's, it varies, but it's, probably, I'm guessing around 30,000 again. You really don't have to worry about that. Like I said, for the test, it's, when you get into commercial aviation, it becomes more of an issue because you're going to be flying through that, especially, when you get into, airlines, they typically will fly through the troposphere all the time because they fly at such high altitudes. The big thing you need to know about, though, is that the troposphere is where the vast majority of our weather is. It doesn't happen in the stratosphere. Occasionally, you'll get a very strong thunderstorm, and thunderstorms will sometimes extend like this image right here. This is probably a building thunderstorm, so it's extending into the stratosphere. That's rare. Those are really strong thunderstorms. Has anybody ever seen a thunderstorm that's just isolated with blue sky all around it? Or seen one at night? Have you seen it at night and how it just goes straight up? It's like a pillar of cloud. If you get out at all and you see a thunderstorm that's off in the distance, you see some flashing lights and like lightning and stuff like that. Take a look at it. What you're going to see is a huge pillar of cloud, and then it's just going to go straight up. That's literally a huge weather factory. That's what a thunderstorm is. It just produces all kinds of really nasty weather. We'll get into it in a second. But in any case, so the thunderstorms will typically, if they're really strong, they'll extend up past into the stratosphere. They'll never go up to the mesosphere. That would be, a massive storm. So, but yeah, all of our weathers, and actually the vast majority of our weather is below 6,000 feet. But the weather that we're concerned with as pilots is, usually is going to be. It's always going to be in the troposphere. Okay. All right. Let's see. Atmospheric circulation. All right. So here, so this is an example of how the atmosphere flows in the Earth. So if the Earth was not rotating, it was just standing still. Let's think about this. So we've got cold air at the poles here and here, right? When air goes up to the poles, what does cold air do? Does it rise or descend? It descends. Okay, so the air descends. So you've got cold air descending here, but you've got other cold air coming in descending. So what happens is it creates this flow pattern on the Earth. And again, this is if the Earth is just standing there still, not moving, not rotating or anything like that. It descends, then it follows this path down. This is where we get a lot of our polar weather systems. You'll hear, like polar vortex, continental polar mass, air mass. That's a term that polar describes where it came from, as opposed to the tropical weather masses that we get. Tropical would be in this area here, whereas polar is going to be up here. But in any case, the air cools, it flows down through here. Like here's the United States right here. It would flow down past us. And that makes sense. When we get those thunderstorms or those huge snowstorms, we typically get it, the cold air anyway is fed from the north, and then it hits that warm tropical weather mass that has lots of moisture in it, and it produces lots of snow. Okay, so anyway, that air flows down, it heats up, and when it heats up, what does hot air do? It rises. Okay, so hot air is rising at the equator, and what it does is it follows this pattern. It goes back up to the north because there's more space for it here. It cools down as it heads north, and then it drops and then follows the surface and comes back down. That's again if the Earth is just totally static. It's just going to follow that pattern. It descends up where it's cold, it rises where it's warm, and it creates this flow pattern. Now, what happens is you have the Earth rotating, and that creates what's called the Coriolis force, which we'll talk about in a second. But just keep this flow, this kind of surface flow in mind. It works in the same ways it's in the southern hemisphere. It does basically the same thing. It cools down, and then it flows up toward the equator, and then it gets hot, it rises, and then it flows back up to the north, or the south pole in this case. And then it gets really cold, descends, and so on and so forth there. So that's called atmospheric circulation. Coriolis force, however, is, let's see here. I don't know if I have to really go over. You guys understand the concept of the weight of a parcel of air. So at sea level, if I were to take an inch square tube and extend it all the way up to the very reaches of space, and I were to hold it in my hand and weigh it, it would weigh 14.7 pounds. That's the weight of the air in that tube. Okay, that's what we're feeling right now, pressing against our bodies, 14.7 pounds per square inch. That's our typical pressure that we feel when we're at the ground at sea level. When you're at 18,000 feet, it's not so much because we're now 18,000 feet higher. We don't have as much air pressing down on us, so now it's only 7.4 pounds. That makes sense when you think about it because the air is less dense up there. Again, up there we don't have as much air. We can't breathe as easily at 18,000 feet. That's when we need oxygen to go all 15,000 feet. So, all right. So this is called. Let's see if I can make that better one than this. Find it here. Yeah, well, here, I'll just read this off the book here. In general, atmospheric circulation theory, areas of low pressure exist over equatorial regions, and areas of high pressure exist over polar regions. That kind of makes sense because, you've got air compressing up here. That's going to produce high pressure. It flows down here. It warms up, so it expands, and so you're going to produce low pressure down here. So typically, not always, but you're going to have low pressure or high pressure systems come from the north, from the polar regions, and then the tropics are going to produce lower pressure regions there. So let's see.
Which one gives you the bad weather? Is it the low pressure?
Low pressure,
Okay.
yeah, will almost always give you bad weather. Not always, I should say, but most of the time it's going to give you. It depends on the strength of the system and how deep that low is, that low pressure is. And it also, how much moisture is in it. There's all kinds of variables that play into it there. So let's go here. Let's talk a little bit about yeah, Coriolis force a little bit. I think they go into this a little bit. But so because the Earth is spinning, here's the Earth right here. This up here is spinning much slower than this down here because it's a huge, wider radius. Okay, so what you have is these sections of the Earth where there's more additional circulation there. So you still have that main circulation like you have here. This is how generally the air flows, but this right here, this it's a kind of a cellular circulation here, where it is in these latitudes here, it's going to kind of circulate there, and then it also creates another one here because again, this is not traveling as fast as the equator. At the equator, if you were to measure your speed through space anyway, it's going to be a lot faster because again, we're at such a wider radius. You can see the radius there is a lot larger than this radius up here. So that's where we get some of those cellular differences in how it rotates there. So they had Coriolis force here. Let's see that again. And so the Coriolis force, I'm surprised they don't show a diagram of this. Coriolis force has to do with the fact that the Earth, because the Earth is rotating, so in this case, the Earth would be rotating, so the Earth is going to be rotating this way right here. Okay, here's the sun right here. And as it rotates, obviously New York gets the first sunlight in the morning, and then we're over here, right there. We'll see our sunrise off to the east here. But because it's rotating, these cells now have a tendency to kind of twist. They're not perfectly, it's not like it just circulates in one area. It circulates across a huge area. So now you have these swirls that take place because of the Earth, and they have a tendency to swirl more closer to the equator than they do up here. So this one may not be quite as much. It might be a little bit tighter there. And then obviously here, they're going to be really tight because it's much slower up here because of the smaller radius there. Does that kind of make sense? I'm throwing a ton of theory, weather theory at you here. So, okay. So that's Coriolis. It's called Coriolis force, and that's why when we flush our toilets, they go a certain they turn to the right when you flush it. A toilet. If you ever looked at a toilet, you flush it. Just if you look at it, it'll rotate to the right. If you're in the southern hemisphere, it actually is in the opposite direction, which is really weird when you go down. Like I go down to Brazil occasionally, and you flush a toilet there, or you would let water out of a tank or something like that, it always rotates in the opposite direction. So that's because of Coriolis force. That's the Earth rotating, and it causes these things to swirl around like that. So, okay, all right. Let's see here, and here. All right, and everybody, we've gone through this before, so I'm just going to kind of fly over this. Everybody understands how a barometer works? Anybody that want a quick review of it? You guys want a quick review of how a barometer works? You guys are good with it? Everybody's good with barometers? Okay. All right. So this is a mechanical barometer, and again, these are it's like a balloon right here. If pressure on the outside decreases, what's going to happen to these aneroid cells here? They're all sealed. What's that? Expand. Yeah, they're going to expand. And so when we expand it, it causes this needle to move down. Actually, it would cause this to move down, which would indicate a lower altitude. There, that's this. They should say it should be lower pressure. It should actually be lower altitude here is what you're seeing there. So. And again, if pressure increases up here, if it increases here, it's going to cause this what? You see, what's that? To shrink. Shrink. Yes, they're going to shrink, right? Because you've got pressure. Just like if I was holding a balloon, and I put it in a sealed room, and I put lots of pressure in the room, the balloon is going to shrink, right? It's going to get smaller. If I put lots of pressure in the room, don't change the pressure in the balloon, it's going to cause it to sink. So because of that, then you're going to a higher altitude. And that's, again, they didn't put it in here. It should say altitude there. Is what it's really reading there. So that's how roughly how a altimeter works in an actual aircraft. Right. Pressure gradient forces. Okay, so if you guys ever watched like the weather reports, and you'll see like these maps. Actually, let me just see if I've got them. Yeah, I do. This is a live map right now, a real map of the weather that we're dealing with right now. So we're obviously right here. Here's a low pressure system. There's actually two low pressure systems, and there's a couple fronts here, which we're going to go over all these symbols and things like that so you understand it. But these lines right here, these are called contour lines or gradient lines or whatever. Notice that they've got a number associated with them. So let me just so there's a number right there. There's another one. There's another one right there. Okay. So what these gradient lines do is they tell you that it's a way of explaining a three-dimensional image to you in 2 dimensions. So if I look at this, let's see if I can find. Okay, here, this is a perfect one right here. So this is a low pressure system right here, and this right here is the hectopascals. So it's 1,000 millibars is what the pressure reading is there, which would be maybe 29 point something degrees or inches of mercury. So it's another measure for barometric pressure. So you can measure barometric pressure, which we in the U.S. we measure it in what? Inches of mercury. Yep. So in the Europe and the rest of the world measures it in millibars. So they have the same meaning. So if this goes down, that means it's lower pressure. So if it drops down to like 980 or 950, that means that the pressure is dropping there. But notice how on this isobar right here that we're looking at, this contour line right here, it's at 1,000. And then the next isobar that's over here is at 1,002. And then this one is at, I think they got these messed up there. So 1,008 is what this is right here. Yeah, you can see it because there's the contour line there, and it followed around. It's back to here. And then there's another one here. It keeps getting larger and larger. So what we're looking at, if you were to actually take this image and flatten it out and make it a three-dimensional image, this would be a valley right here. Okay, it's a low pressure valley is what we're looking at. You've got the lowest portion up here, and notice all the bad weather here. You've got all the rain. You can see some storms in there. Again, over here, this is low pressure yet. So we've got some other, and plus there's some fronts here. That's a stationary, by the way. And then we've got, here's another low pressure system right here, right next to a relatively high pressure system. That's the one thing you'll learn is that, that H doesn't give you a number. It just is telling you that the pressure here is higher relative to the low pressure next to it right there. Okay, so that's why this is the highest pressure in this region, so they put a high pressure there. Same with this over here. You can see that there's kind of a contour line right there. That's a low pressure, even though it's not as deep a low as this one right here. That one's at 1,000 millibars. This one's only at 1,012, which is not terribly low, and that's why we're not seeing probably as much bad weather here. And then we've got some weather here. But you could start looking at these charts when you start looking at aviation weather reports. You can go on to weather.gov. They've got aviation weather reports there. I've got tons of resources on the SIA site that you can go to look at weather. This one right here I happen to be at is the flight service that you can get registered for, and you can use that. It's a very useful site. So, all right, so those are contour lines there, and that's something you'll see a lot in aviation. there. Let's see here. Here. This is another one. Again, you've got contour lines there. This is a current weather depiction. So somebody actually drew this out basically. You can see there's that low pressure there. They don't show the radar returns here. They just show what's they're thinking the weather's going to be doing. So again, we get into this in a minute here. So. Let's see here. Okay, wind currents. So let's actually go back to this one here. So one of the things you'll learn in aviation weather is, this is on 12-7, is that there is a certain flow of the air around low or high pressure systems. So in low pressure systems, they do what's it's called an anticyclonic. So it's actually going to flow in like this way right here. Whereas high pressure, they're going to rotate generally clockwise. That's typically how the weather or the winds are going to flow around high pressure. Like here's a high pressure system. Maybe we can even find a map that shows that right now. So let's just keep this in mind right here. Over Minneapolis right here, there's a low pressure system right there between Minneapolis and Superior. Keep that in mind because we're going to bring up another map that's going to show us how the winds operate around a low pressure and how they operate around a high pressure conversely. And so those are flows. So in a low pressure system, though, the air is typically flowing in. So like here, if we were to check the winds, they would probably be flowing in, this way right here into this this low pressure right here. Again, it's low pressure, so it's bringing in, it's sucking in the air because there's relatively low pressure, just like a vacuum cleaner. When you turn it on a vacuum cleaner, it brings in air, and that's what causes it to create suction. So think of a low pressure as a vacuum, and a high pressure as something that's blowing out air. So these are typically going to be like a high pressure system. They're going to be they're oftentimes called high pressure ridges, low pressure valleys, low pressure. Gosh, I don't know those other terms that they use for them, but typically high pressure is usually referred to as a high pressure ridge, as in a ridge of geographical characteristic of the Earth or something like that. So, and that's because air is, bunching up there. And so with high pressure systems, conversely, those the air there is actually flowing outward. So it's going to flow like this. If you look at the surface winds, there's other things that modify the surface winds, but they're typically going to flow outward from a high. So if I was like right here, I would expect to have winds in this case probably out of the east here, or because of the terrain features that might be modified. There's also Coriolis spores, which is going to cause that to modify even more. We'll get into that too. So let's see. Let's talk about what high and low pressure does to a performance on a plane. So if I take off from an airport, let's say it's at sea level, and the pressure is really low, what is that going to do to my performance?
It's going to enhance it because you don't need you don't need a lot of runway to take off, and it's you'll take off at a little bit more.
On a low pressure system? Okay.
Wait.
Yeah, just the opposite.
Just the opposite.
Yeah. It's really confusing because this is one of those things that gets a lot of people and has gotten me several times. High pressure means the air is denser, right? So you've got more pressure on the aircraft. There's a lot more air going in there, a lot more molecules to hit the airplane and go in there. Yes.
So just to expand on that, it'd be less lift to take off.
Yes, more runway needed. Yeah, for a low pressure system.
Oops, I just got those through.
Yeah, I know, and it's easy to do, and that's one of the things you when you take the test, be thinking in terms of, if you have a good concept of what high pressure and low pressure is, you'll do better because you'll catch little things like that, and it gets everybody. There are some pilots that do not even know the difference between a high and low pressure system. They know that because of years of flying, they know that low pressure systems typically bring, worse weather, but they don't know really the difference between it. So, low pressure, think of Mount Everest. High pressure, think of, sitting on the beaches of California and relaxing there. You're at sea level. There's more pressure. There's more, that column of air is longer, it's taller, so you've got more pressure pressing on you there. So again, high pressure, air is denser. The plane performs better. The engine performs better because of high pressure, because there's more air for it to breathe, just like we do. If I were to go up and climb up Mount Everest, I would have a really difficult time climbing beyond like 15,000 feet because the air is very thin up there. There's not as many particles of air, and the pressure isn't as much, so it's harder for me to breathe. Think of Mount Everest when you think of low. And that's the thing that really blows your mind, because you're talking high altitude is low pressure, low altitude is high pressure. And that's where I think, a lot of times you get those things confused or mixed up. So, but if you can understand that concept, you'll do better with it. So yeah. So conversely, what's high pressure going to do when we take off from? Yep.
You can produce more lift and performs better.
Yep. Perfect. All right. So I'm taking off from Baraboo right now. Let's say the altimeter setting is the same as it is in Denver. And we take off from both airports. Is it the plane going to act any differently in Denver than it would be in Baraboo? Again, I said the altimeter the altimeter setting is the same. I didn't say that the pressure is the same. I said the altimeter setting is the same. Yep.
If I remember correctly, I think Denver has usually higher air pressure, so Denver would be better.
Why would it have higher air pressure?
I believe it is. Actually, no, it'd be lower because it's usually it's Denver and that area is just a lot higher.
It's higher, yeah. So there's not as much pressure on it. Again, there's so many things that you have to think about when you answer those questions. Just make sure you've got altitude, pressure, and all that stuff correct in your mind when you answer those questions that relate to, altimeter settings, pressure settings. So the answer would be, well, first off, Baraboo's at a much lower altitude, like 4,000 feet lower than Denver. So the pressure here is going to be higher because there's more weight of the air on it. There's, it's got a higher, taller column of air, so the air pressure is going to be higher. So the plane at Baraboo is going to perform better than the one in Denver, because the Denver one is up higher, but it's at a lower pressure because the column is smaller. Does that kind of make sense? All right. All right. So, okay. Convective turbulence and avoidance. Let's see. Convective turbulence. Let's see. Okay. So the Earth typically heats. Let's see. There's this that answers that question we were just on there. And yeah, I think this same situation here, the difference, and it's pronounced. This is the problem that we were just talking about. At sea level, the pressure is going to be much higher, so you get better performance all the way around. At a higher altitude, 8,000 feet, because there's less, air up there, the plane has to work a lot harder to build, and it's hugely noticeable. When I fly out west, the runways out there are typically a lot longer, than a same size airport, but the runway is going to be a lot longer because they realize that, you need more runway for a typical aircraft to take off. And again, what we talked about before, this is where a lot of pilots get into trouble when they take off on a hot, humid day. They wind up taking off, staying close to the runway, but then they never make it off out of ground effect, and they just usually end up in the farmer's field someplace out here because they didn't take that into the performance calculations there. So airflows. Let's see, here's an unrestricted view of those isobars that we talked about. Low pressure, there's another diagram of that. Let's see, high pressure, There again, we've got this. Go back to these, I think, too. Here's a high pressure ridge. Again, high pressure you usually associate as a ridge. Get to, yeah, okay, so here's a good diagram right here, where you have the sun is out a hot day, and let's say a farmer just plowed their field right here. So you've got, excuse me, relatively dark earth right here. The sun hits that. What does it do to that dark earth? Yeah, it heats it up, and that air does what?
You know,
It rises. So if I'm flying through this, I'm going to hit that turbulence. It's like if you were to actually see this in real life and actually watch the air move, it would look like a boiling water, bubbles of hot water moving up, bubbles of hot air moving, rising through there, and you're flying through that. So you're going to have some turbulence with it.
At certain angles in the summer, you can see that on the road too.
Yes, yes, you
Lines
can.
up.
Yep. You'll see like areas like distortions in the air. That's where mirages essentially come from. It's a distortion of the light. What's
That
that?
comes on football fields,
Oh, really?
Turf football fields.
Uh-huh.
Really have some days.
Really?
Yeah.
Yeah, that would be brutal training like that. So, but yeah, so that's essentially you're seeing the beginnings of that air rising as it comes up, and the plane at some point is going to probably fly through that. That's why we typically want to fly a little bit higher to get. At some point, this air is going to rise and then cool, and then it's going to be at the temperature of the surrounding air, and then it becomes much more stable. And we talk about that again here in a second as well when we get into the temperature dew point. But that we typically want to fly above that area, and it could be as low as 3,000 feet. It could be as high as 20,000 feet, where the air cools down enough where those convective currents don't cause it. What other types of convection can we have like this? So we've got, this is just a farmer's field, but what other types of convective currents can we, how else can air be shifted? When I say convection, does anyone know what you guys have heard of convection microwave ovens? That term before. So what they do is they swirl air inside the microwave. They circulate it around. Think of of convection as circulation. Okay. So convection, we've got again here. This is just hot ground. The sun heats it. The air rises. But there are other ways of creating convection. Can you think of it?
Snow melting on a hot day.
Yeah, that could do it. Yeah. Another thing that can cause convection is terrain, like a mountain. So if you have air, let's say we've got, let me draw this out here. So let's say you've got a mountain like right here, and you've got the wind is flowing this way right here. What's going to happen is the wind hits that and it flows up and down. That's creating convection. Okay, that's another way of creating convection. Another way to create convection is, let's say you've got a body of water right here, and then you've got all these trees right here. I'm good at drawing trees, so you guys have to bear with me. Let's say these are pines, so it's it's a dense pine forest right here. So what will happen is you've got hot air rising here. What happens if the wind is flowing this way, it can actually cause the air to convect down in this direction to actually cool down because it's over a body of cool water, let's say. So it causes it to cool, and it goes back over the air and it creates a convection there. Yeah, so this works the same way as again the heating of the dirt or something like that. A parking lot can generate a lot of convective currents. This is on a larger scale, typically, which we're going to see here. But that's all those things are going to create disturbances in the atmosphere that you have to be aware of. Now, this happens on a large scale when you head out to the oceans or big lakes. When you fly on big lakes, you have to be aware of the fact that there could be currents that are flowing down, not really severe, but they are enough to cause some turbulence in the plane. So one of the things that you'll hear a lot in aviation is that the sun is the driving force. And this is something we've known for years. The sun drives the planet's weather. And that's because when the sun hits the earth, it heats up things. Because it heats up air, expands, and it creates these circulatory patterns. The earth is rotating, it's creating patterns and things like that. All of these things basically conspire to create a habitable planet that we have here. And again, it's all a result of that sun heating the earth. It's warming up the land masses. It's cooling. It's not, when it hits, the sun hits the oceans, it's not as intense. So the oceans are relatively cooler than land masses are. Land masses typically will heat up a lot more. Okay. So obstructions in wind. Does everybody understand that part of it? Right. So obstructions. Let's see. Yeah, this is a good diagram here of convective heating. You've got heating of the air. You've got these little bubbles of hot, warm air that rise up. And it's not as neat as this. Obviously, there's like little tiny bubbles in here. And so you have this turbulent flight. Whereas if you fly up typically above the tops of the clouds there, you're going to have a nice smooth ride on there. And there's a reason for that. And I'll show you how to actually predict that. You just need two numbers to actually predict where that level is on there. So, okay, let's go here. So this is the thing I was talking about, where you've got a body of cool water and a bunch of pine trees or whatever, farmer's field or something like that. So this creates a pattern here, a wind pattern. It just circulates down. You've got, again, warm air, sun hits this right here, warms up, the air rises just like it does at the equator. That air rises, it goes through up here, it comes back down. As it starts cooling, it descends, and it creates a sea breeze right here. So, and again, you can have pretty turbulent, ride in this area right here. And same thing happens at night. It just reverses the flow, because this has to do with, how the differences in thermal capacity of land and water. You have different thermal capacities. What I mean by that is they have different rates of that they can heat up or cool down. And because of that, it creates a difference here. And what happens typically at night is you've got the air, the water has got so the water has a greater thermal capacity. So it's a little bit more stable in its temperature throughout an entire day or several days. It doesn't shift like the land. You could touch a pavement at night and it's cool, and then the next morning or in the afternoon you could touch it and you could burn your hand. So that has the thermal properties are a lot faster, I guess, than they are the water. And because of that, you have return circulatory pattern right here. Again, this maybe roughly the temperature of the water is only 49, 50 degrees, but the temperature of the land during the day could be as much as like 90 degrees, and then at night it drops to 50 degrees or something like that. And that's where you get these circular flows like that. Okay. So here's a good example of what we call orographic features, or like heating and stuff like that. We've got a parking lot right here. Air warms up in the parking lot, it rises. This is your glide slope to the runway. That when you hit that parking lot, the air above it, and this is assuming that there's no wind, it's going to push your airplane up. The tendency then for the pilot would be to push the nose down. They'll glide through their flight path here and descend lower. So those types of features at some airports are really prominent. At Reedsburg here, they've got a huge parking lot. So when you're coming in, especially if you're coming in on a real shallow approach, you're going to definitely feel that on a hot day. It's gonna cause the plane to rise, and then again, the tendency you got to watch out for is that you're going to push the nose down to get back on your glide path, and then descend through the glide path here. So those are the types of things that you have to be aware of. And then there's also let's see here. Obstructions. So you could have hangars, it could be buildings, or would it be whatever. But when you have wind flowing across these buildings or whatever it is, it could be towers or something like that. It could be, a bluff or something like that. What happens is as wind flows across it, so if the wind is going this way at altitude, let's say it's flowing nice and smooth up here, but because when that wind hits the backside of this right here, it has to go over the top of it, and it creates these eddies right here. And so we get these like swirls of air all the way around here. Here's another one that's swirling a different way. These can be really pronounced in higher wind conditions. Maybe the ride above here at 2,000 feet, it's totally smooth, but down on the earth itself, it's going to be, on the airport runway, it's going to be extremely turbulent. So those are things you have to be aware of. And obviously, is it going to be worse when the wind is higher, or is it going to be worse when the wind is lower speed? Yeah, when you have a higher wind. Yep. When the wind is really strong, it creates stronger eddies, and it's enough where it could, if you're not careful, you could have a tough time coming to the landing there. So, and obviously how tall it is. If this was a really large hangar, right here, let's say, obviously this is going to create much stronger. This hangar, a big hangar like this right here, is going to create much more turbulence right there on the runway than a smaller hangar. And then also, if it's really low to the ground, the lower the ground it is, the less likely it's going to cause as much problems. So, and again, it could be a building, it could be a terrain feature out west. Obviously, there's mountains, and the stronger the winds out there, the more careful you have to be. There have been a number of incidents where pilots have gotten into real bad situations because they, approached a mountain. Let's just see if it's here. Here. So let's say we've got a mountain here, and you've got wind on this side blowing here. Here, obviously it's going to go up, and then it's going to, what it's going to do here is it's going to, there's a little bit of burbling here that comes across here. It's going to kind of create a little bit of turbulence. If I'm approaching from this direction right here, and I want to, climb up here, I'm going to have to deal with those winds pushing me down right there, because they're actually, you have several of them here. They're all going to do the same thing. They're going to hit that peak, and then they're going to start bending down. So pilots have gotten themselves into real trouble in this area right here, where they get too close to the mountain, and they, wind up, crashing into the mountain, or they have to turn around or something like that. So this, by the way, is you'll hear a term windward and leeward side of a mountain. The windward side is the side that the wind is coming from. This would be the windward side right here, windward out there. And this is called the leeward side. That's the opposite side where the wind is going to on the mountain. So this is on the leeward side of the mountain. This is where you're going to have trouble. That's why we always, whenever we approach a mountain, if we can't get over it, or we're going to be really close to the top of the peak of it, we always come in at a 45-degree angle, and that way we can always turn away from it if we have to at a 45. We don't want to go, straight toward a mountain and assume we can make it over the top and then wind up having to, doing something stupid. And it happens with professional pilots. It's not something that happens to new pilots. It can happen to new pilots, but it happens to very experienced pilots. And again, it's just a very basic understanding of how wind flows around terrain features here. So, ready to understand that? Here. Okay, so yeah, I won't go into some of this other stuff you'll be able to read here. I'm not going to get into that. So wind shear is another item that obviously pilots have to be really careful with. So this actually just describes what I was saying there. If you got the leeward side, the leeward side, you get all these turbulences here. So the type of geographic turbulence that's created. You've got all this uneven terrain. It creates all these little eddies right here and swirls. If you're flying through this, it's going to be a rough flight, especially when it's all right. So another type of turbulence that we can encounter is what's called a microburst. Typically, they're seen around thunderstorms. So let's. I wish we could have talked about this a little later when we actually talk about thunderstorms, but I'll bring it up right now. So how a thunderstorm works, there's 4 stages of thunderstorm. And we're going to go into this a little bit more later, so if you don't understand it, don't worry about it. But in the first stage, you need a lifting action, and you need instability, and you need moisture for a thunderstorm. So this is a cumulus cloud right here. They're the big, often kind of like the clouds we have today. Those are cumulus clouds. You can look at them; they're kind of torn, shredded, and they look like cotton candy almost. What happens is you've got, let's say, the end of this runway, we've got lots of heat flowing up from this runway, a lifting action, and it causes this cloud to grow in size. And as it grows in size, it essentially builds more energy. The more moisture you feed it, the more heat that goes into it, the more energy that has. And these can grow up to like 60,000 feet. These cumulus clouds. This would be a cumulonimbus cloud, and it would keep growing. And in a case, what happens is this would be let's start out with, you've got this is what's called the building phase of a thunderstorm. So you've got this air mass that's warming up these clouds. It creates this billowing effect. And again, this could go up to like 60,000 feet. What happens at some point is the temperature cools down for the air, the bubbles of air that are flowing up. They cool down to the surrounding air temperature, and then it stops growing. Has anybody ever seen an anvil shape to a thunderstorm? You have seen it before? Yeah, if you look at a thunderstorm that's growing, especially when it gets close to the mature stage, you'll see this what looks like an anvil right here, like this. The anvil is always pointing in the direction that the air is pushing, so that this whole system right here is moving this way. This storm is moving this way. So in any case, what happens is that the air keeps building. It's hot air going up, and then it cools because all of this air around it is relatively cool, and it winds up cooling that air down. That's where the top of the thunderstorm is. And then it cools down so much, it starts descending. Okay, and that's where we get our microburst here. So, and these descents can be extremely rapid. And that's what happens in a downdraft. Again, you can have them without a thunderstorm, but typically microbursts are almost always associated with thunderstorms. That's where you're going to see them. There have been a bunch of notable aviation accidents. There was one major accident, commercial airline, and I think it was L1011. I could be wrong on that. Down in the south someplace, like around Atlanta, where they ran into a microburst. And what it is, it's that descending air from the mature thunderstorm, and it wound up. The plane was either taken off or coming into land, and it hit that microburst, and that air was coming down at it could have been as much as 6,000 feet per minute. And it caused the plane basically to go right into the ground. As a number of people did survive, but as a matter of fact, I know one of the guys that survived that crash. He was in it. And, a little description of him, but in any case, so that's something that can happen. And with small planes, it's even more deadly. You got to be really careful with, because those currents are so strong. You can give the plane full power, and you will not be able to climb out. You won't have enough power to climb through that microburst there. So
So in that case, would you want to plan in like a field in this way for the cloud to pass? Or
I mean,
or is it just like preventative, like you should know that there's a storm coming, so you probably shouldn't go out?
yes, but yes, you're right. That's the better way of dealing with it. But if you're one of those unfortunate people that get, vectored into something like this, which is rare, but it can happen. When thunderstorms are subsiding, maybe they'll allow more traffic to flow in. I've had this happen before with me where I've flown in and around thunderstorms. I haven't flown in them, I've flown under them. And ATC was totally fine with that. But you could still have a real strong downdraft. If, at that point, it's almost too late to turn around when you get in it. The only thing you can do at that point is apply full power and do your best to stay in the air. You just get through it. Now, here's the thing about it. If you get caught in a downdraft like this, once you get on the other side of it, it's not going to be as bad. It's still not great. You can see here this plane, drops down dramatically right here at the center of the downdraft. And then as it gets past it, these downdrafts only last about 5 to 15 minutes. They are not going to be there forever. But hopefully you get on the backside of it, and then you can start doing a slow climb out here. You're going to have a tailwind on this side, because what happens is that downdraft, flows down like this and hits the ground, and then goes out like this. It flows out like that, and because of that, you're going from a tailwind right here, or a headwind right here, which you're going to have really good performance. On the backside of the microburst, you're going to have a tailwind, which is getting close. Now we're talking about wind shear. You're going from maybe, let's say this is like 20 knots right here. The outflow is 20 knots in both directions here. So this is 20 knots here. This is 20 knots in this direction right here, and 20 knots in this direction. So if you're flying at 70 knots and your stall speed is 50 knots, here as you're coming in, it's going to feel like you've got a you've got a good headwind, so you'll have plenty of lift and be all right. But you get here, it's going to be nothing, but you've got the air flowing down, pushing you down. And then on the outflow side of it, you've now got a tailwind, so you're going to be really close to stall if in that situation. Now, if you're one of those people that have plenty of power in the aircraft, again, full power, you can move yourself out of that dangerous area there, and then start climbing again. So yeah, the only thing you can do, I would not risk turning around and something like that, if that's what you're asking.
No, I was asking like if you could, like the best idea would just be like go down and try to find a field or something like that.
You can. It may not be necessary, especially if it's a minor microburst or minor or small microburst. Sometimes they don't last like a real. They're not like a huge area. You're maybe only talking, a mile or two, or sometimes even less than that. So if you can get through that before you hit the ground, then you're all right. Now, if you're really close to the ground, you may be stuck with coming into land, or having to land in a field or something like that. But if let's say you're at 5,000 feet here, and it starts pushing you down really fast, I wouldn't give up, because by the time you get down to maybe 1,000 feet, you may have been past the dangerous point, and then you can keep on flying through there. Does that make sense? Right. So that's wind shear. So wind shear, by the way, is any change in the direction or speed of the wind. Okay, so that's what wind shear is. And it's usually like 6 knots difference. So let me talk about that a second, just to make sure you understand that. So here. So let's say we've got wind, we're flying at let's say 1,000 feet right here. 1,000 feet. Okay, and we've got winds at 10 knots. Out of 270 degrees. All right, and then at some point, whatever it may be, could be convective currents, it could be a microburst or something like that. Who knows? But there's a number of things that can cause this. The change now is now only 4 knots, or the wind is now 4 knots at this point right here. This can happen really quick, especially in turbulent conditions. You go from 10 knot, in this case, let's say we've got let's say we're going this way right here. Here's our plane right here. Yeah, we're going this way. So now we've got, in this case, we've got a relatively small tailwind or a headwind, and now we're going to be heading into a stronger headwind. So what would be worse here would be to be on this side. So here's the plane going this way right here. Okay. And it's going from a 10 knot. So it's going from a 10 knot tailwind to a 4 knot tailwind. So that's a change of 6 knots, right? Think about this here. So we've got a headwind. Here we've got a head knot, headwind of 4 knots. And on this side of the line here, 10 knots. And here, this way, we've got 10 knots going here. This is 10 here, this direction. So we get a 10 knot tailwind. We're now dropping to a 4 knot. So let me just review this. It's a little bit better here. All right, so let's say we've got a plane. We got on this side right here. Here's our plane. Okay, we've got a 10 knot headwind here. And we've got a 4 knot here. So what's going to happen as the plane goes in this direction, whatever, it's experienced a 10 knot headwind when it crosses this line. And again, it could be anything that causes it. It could be, even heating of the Earth's surface. It could be just the convection, flying close to like a body of water or something like that. But the wind changes here. That's what we call wind shear. So as the plane comes in, it's got a 10 knot headwind. Let's say our stall speed is 40 knots in this, and we're the S speed is 40 knots, and we're traveling at 50 knots right here. So as we move along here, we've got a 10 knot headwind, so we got plenty of cushion here. Our stall speed, we're at 50 knots. We've got plenty of room here to continue on. But when we hit this point right here where the headwind drops to 4 knots, what's going to happen is we're going to essentially lose 6 knots of that headwind. So now we're getting much closer to our stall speed. So now we're within 4 knots that stall speed. So it's really close. So this is why when you're in really turbulent air and you're coming into land, it's not a problem when you're up high, flying at 7,000 to 8,000 feet. It's typically you're flying at cruise speeds and you're not flying around your stall speed. But the problem arises when you come into land. So if this is a runway right here, because of that difference in airspeed there, that wind shear, the plane is going to lose, some lift. It's not, we don't have as much air blowing against it. The wings produces as much lift, and so the airplane's going to descend a lot faster. And that's the danger of wind shear. It's when you're really close to the ground. When you're up in the air, it's just a really unpleasant life. And there can be circumstances where wind shear is so strong that it could damage an aircraft. I've never heard of anything like that, but it can happen with a small airplane. That is, it's not something that you typically see there. So, does that make sense? That's good. So, all right. Okay, let me just talk about a couple other things here. So I like this diagram right here. They don't have it in the book, but this kind of describes what happens when you have air, getting moved up a surface right here around a mountain, for instance. So you've got relatively warm air. It moves up, and as it gets pushed up the mountain, the side of the mountain, obviously up here, we know from past experience, we've talked about this before, how as you climb, the temperature goes up or down. It goes down, right? It gets colder as we climb. That's what's happening here. The air is getting pushed up. You've got wind blowing this air up the side of the mountain. As it goes up the mountain, it gets colder and colder. And so you get these change in temperature. It modifies that air mass. And then on the backside, it does just the opposite. It starts getting, cooler. Or so it starts getting warmer as it descends there. Guys, let's take a quick break because I've been throwing a ton of stuff at you. Let's do like a 5-minute break. Give you guys a chance to breathe a little bit, and then we'll take off this chapter and move on to the next one there. Yeah. Does anybody have any questions at all on any of that stuff?
I was wondering something.
Yeah.
So I got Forklight installed on my little tablet.
Excellent.
How can you see other planes, like when they're flying? Do you know?
Yeah, you betcha. So we're going to go to here, and there should be, let's see. Other plane. Okay, so I think actually we're talking about layers here. Give you a second to get through here. Here we go. There should be. So this will show you there should be ADSB traffic. I thought it was this right here. Now, if you want to get ADSB from your own aircraft or from other aircraft,
Yeah.
you're typically going to get that with another. You'll have to have another device like an ADSB receiver, and then that'll work in here. So that would be what you would do here is. So what you're going to do there is if you need an ADSB, and you can get some really inexpensive ADSB receivers. Once you have that, what you do here is you go to this and you click on devices, and then you connect to the device here, and that's going to pick up, and it'll pick up jets all the way up. Yeah, I mean, you'll actually see traffic from all over, probably within, I'd say 40 miles if you're jet traffic, small planes, everything. Actually, if you get down to Madison sometime and you have that with the ADSB receiver,
Isn't that a required, like a required sticker to fly?
not
No.
for Class G airspace, and let's see, I don't think it's. Yeah, you do need a Class E airspace. No, you don't need it in Class E airspace. You need it in Class A airspace, B airspace, which is busy airports. Class Charlie airspace, which is like Milwaukee, Madison, or Milwaukee and Madison, that is. You need a Class D airspace, which would be like La Crosse, Appleton, Oshkosh, things like that. And I'm not actually even sure you need a Class D. I might check that. So I can look it up in the regs, but essentially, yeah. But if you're all flying around here, you don't need it. Like if you're flying around Pittsburgh, it's that's the ADSB out. Now, there's two types of ADSB. There's ADSB in and ADSB out. ADSB in is composed of two different parts. There is the FISB, which is Flight Information Service, and then there's TISB, which is Traffic Information Service. So the flight information is going to be like your weather products, and you can look up, I could, on there as I'm flying, I can look at the weather in Madison, or where, say I'm flying to Green Bay, and I want to see what the current METARs are at Green Bay. I can look it up on there, and that's free. It doesn't cost anything. You don't have to pay any cellular fees or anything like that. It just gets it from ground stations that are being transmitted to it, and then you'll see all that traffic in there as well. Yeah, it is. It is. The FAA did this. They had this back in the 90s. They were talking about this next gen aviation, things that pilots could really use. They experimented with it up in Alaska, and it really saved a lot of lives. Because pilots just didn't know what the weather was at their destination. They take off. They knew what the weather was when they took off, because they call the destination and say, "Hey, what's your weather level like?" They'd say, "Oh, it's 1,000 over the answer," something like that. But when they got up in the air, they didn't know what the weather was until they got really close. This, allows them to download weather for any airport. They can actually bring it up and see what it is right in the flight there. So it's and then you can see radar returns. They got, I think, lightning now. They've added to it, icing conditions. There's all kinds of ADS-B products that don't cost a cent. So you don't have to buy Sirius subscription, although they have some additional products that are put in place as well. So, yeah, there's a low-cost ADS-B receiver you can get. If you don't mind tinkering with electronics a little bit, I can even help out with it if some of you guys want an ADS-B receiver. I can build you one. I think it costs less than $90 or maybe even $50. And like I said, you'll be able to pick up traffic from all over in about a 40-mile radius. So here you'll see commercial jets flying up to Minneapolis, ones that are flying transcontinental, things like that. So it'll tell you what their end number is and how fast they're going, and details about the flight itself. Yeah, and that's all from ADS-B. It's cool. Yeah, it's pretty handy, and it's actually saved a lot of lives, I think. I think we talked about it a little bit here, the FISB and TISB. That's ADS-B in. ADS-B out is your aircraft transmitting this.
Yeah, the information.
Yes, yeah. It
So
says
like
out
your
here.
altitude and then your what else is it, like your speed, right?
Yeah, it gives you latitude, longitude. It's sending out this
Squawk.
There's another term for it. It's a squawk. You're thinking like a transponder.
Yeah.
A transponder will send out a squawk. But there's another term for it. It's just basically a packet of information. It's got your airspeed, your altitude, your pressure altitude, that is, because it doesn't know. And then it's got your latitude and longitude, which is really important. It needs to know where you're at on the planet Earth. And I think there's a couple other pieces of information. Your ID for that ADS-B out unit, and that's why you'll never see a portable ADS-B out. It has to be installed in an aircraft. So think of ADS-B in and out as how it relates to you inside the aircraft. ADS-B in is bringing in information. ADS-B out is sending out information to other aircraft. If I'm flying over here and you're over here, your ADS-B unit's going to maybe ping mine. I'll actually hear yours over here, and I'll get the direct call from your ADS-B unit. I'll know that you're right there and you're flying in this direction, and that I should be looking out for you. There's more to it than that. They've got ground stations that are constantly uplinking data to those planes, those ADS-B units as well. So now you're not only seeing airplanes that have ADS-B, but if there's some guy down here that doesn't have an ADS-B unit, but he's being picked up on Madison radar, Green Bay radar, or something like that, that information gets sent to ground stations, and they send it back up to the so that's where you see the full picture. You're not seeing just the planes that have ADS-B, and that's why they probably are a little lax on how much ADS-B is implemented, because it does cost. It probably costs about anywhere from $1,500 to maybe $10,000 to put an ADS-B out unit. An ADS-B in unit is $50. You can spend $1,000 on an ADS-B in, but you don't have to. And again, you don't need any cellular towers or anything like that. It's just the airspace system that they've So yeah, we need to have this because it's good for safety.
Yeah.
Did that answer your
Well,
question?
yes, it is.
Perfect. Yeah. Yeah. I might actually have a course on ForeFlight
Yeah.
at some point. Yeah. Because there's, I think we'll see a lot of pilots in there because there's so much that you can do with ForeFlight. It's a really good product there. You guys, I'm going to just go to the bathroom real quick and I'll be back in just a second. I have actually for a little bit longer.
Yeah, the 200 value. Oh, wait, what? It's definitely expensive.
Yeah.
I mean, the only reason I would just seems kind of experimental. It looks like a prototype, probably. Oh, so some planes just.
It's like the only real one to look.
The rest just look like normal. Generally, it's
Short or general aviation.
there's a few sport ones there.
Oh, this is like,
Every time I look at those, I'm like, I used to forget that planes are actually that expensive.
Yeah, it's like the price of a new Charger.
Yeah. It's sometimes, I mean, like just getting a nice SUV can cost more than getting a plane.
Some of them are like 30 to 40 grand.
Yeah.
I don't
Or
know.
like getting like a really nice GMC. It's a few $1,000 almost.
Yeah. One of these projects.
I swear, no, like that's it.
I don't know.
I was supposed to start on home again, but
Who would you rather have, an expensive car or an expensive or a okay plane?
the weekend after.
I'd say expensive car because okay planes will probably have way more in maintenance.
Yeah. Also, cars just give you overall more efficient, useful.
Say 1%. Okay. All right. I flew through that, guys. You guys have to have some questions. Does everything kind of make sense at all? Or, and you guys are reading this? Yeah, tell you
What type of damage could windshield cause? Like skin wrinkling or?
Well, if you get severe enough turbulence, I mean, if it's really severe, it could wind up warping the wings. It's unlikely it would actually break apart if you're flying a Cessna.
So that like warp them downwards or?
It depends on the type of turbulence, So if you're in a downdraft, that might warp the wings down. Typically, because you're flying through turbulence, you're imposing loads of the aircraft. It's bending, the wings are bending back and forth like this. Have you ever been on an airliner at all? Okay, so have you ever looked at the window and looked at the wings?
Yeah, wings are like.
Yeah, they're doing this. They're flapping around a little bit. Have you ever seen that before? It's kind of unnerving. But I'll tell you what, the Boeing 737, I think they tested a stress test on it. They did what they called an ultimate stress test. They actually put hydraulic controls on it. They mounted the air fuselage to the ground, right? And then they put this hydraulic unit on it, and they bent it, I think, 50 feet, at least 50 feet before it didn't fail. It just, some spars snapped in it, but it still was able to fly. That's, 50 feet. That's a lot of distance there. So it's, at some point it would break, but what happens with aircraft is, like when we're flying, and you'll see it with small aircraft, the wings will do this. They'll flex a little bit. They're designed to do that. They're designed to flex up and down like that. Really, what we're concerned about is the weight of the aircraft. If I take this and bounce it, so there's more. Yeah,
I'm sure that's happened before.
Well, believe it or not, with small planes, they just don't break up. I think there was one incident where a guy intentionally took a 152 up, and he did get it to break, and even then, it was it didn't break up like he did. Other types of aircraft, like Beech Barons and things like that, those are heavier aircraft. Those have had in-flight breakups. But the 172, if you're in one of those, or 152, it would really be hard to overstress the wings to the point where something broke on the wings or something like that. Yeah.
I'm pretty sure the 7 the wings are actually designed. It's actually
Yes. Yeah, you're right. You're right. Yeah. It's a really weird feeling when you look out the window and you see those wings as the plane takes off. the wings kind of bend up like that because they're supporting all that load of the aircraft. But in just even the old style airliners, those wings were flopping around like this. Even in light turbulence, they'll be flopping around a little bit. And they're designed to do that because again, you're imposing a load on them when you're flying through the air. If you've got like a downdraft or something like that, it causes the plane to go down. But at some point, you're going to fly through that downdraft, and it's going to cause the plane to lift up, and that's where you cause those excess loads on the Yep.
So another question: what would you say would be a good like first plane? Because we Tim were looking at the one of the magazines, and it was showing airplanes for sale.
Yeah. So you have to talk to the pilots that own one of them. I've always liked the Cessna 150. It's a low cost plane. The 152, that's what we have. And that's what you guys are flying with me. After we get done with the class, I'll take all you guys up in the 150 or if you want to find the twin Comanche, it's up to you guys. I'll leave it up to you. And then I have the Chief as well, but that's not a really good trainer. But in any case, 150 is a good bet, but there are a lot of other ones that are really good. There's, I think, and I can't think of them. Obviously, if you can get your hands on a Cherokee, but they're super expensive. It depends on how much income you have, how much money you have to spend on it. If you had let's say you had a budget around $40,000, that could get you maybe a 172 with an engine run out. It's not going to look pretty. The paint on it's going to look horrible. This is my tip to everybody who asks me about buying an aircraft. The first thing I tell them is don't look at the paint job. Just completely ignore the paint job. So many pilots, when they buy, they look at the paint and they say, oh, I don't want to buy that. You can save yourself a boatload of money by getting a plane that looks, that's beat up and stuff like that, and save a ton. So yeah.
So about that, how much would it be to get like a new paint coat on?
Well, if you're willing to do some work yourself alongside a mechanic, an approved mechanic, you could save quite a bit of money. But typically, if you were to send out like a Cessna 150, you're probably going to spend around $10,000 to actually have it painted by a professional shop where you don't do anything. But if you're willing to put in the time and do the stripping of the paint and work with them, and then maybe do some of the painting yourself, you can cut that down to maybe like $3,000, in paint, because the cost there is going to be in the paint itself. So it would cost a little bit more, I think, for a 172 or something like that. Just to give you an idea, I had my twin Comanche done here at the Reedsburg Airport. They had a paint shop, and they may still operate here. And I think it was only $10,000 for that. And it's a beautiful paint job. I've had a lot of people come up to me and comment to me how nice it looks. It looks like a brand new aircraft. So, again, it depends on the size of the plane. Nowadays, those prices, all that stuff is gone. This is back maybe 10 years ago. So, but again, it really depends on the aircraft itself. If you can do it yourself, you'll save a ton of money. And it's actually kind of fun if you don't mind stripping paint, which sometimes is pleasant. But if you can get through that part of it, you can save quite a bit. That's the biggest issue there is you're disposing of chemicals and things like that.
Yeah, it smells bad.
Yeah, you'd wear a respirator and stuff like that. So
Yes, I built fix up a bit of frost on my dad's pickup.
Yeah.
It was tiring, but
it
did feel very rewarding afterward.
Yes. Oh yeah. When you get it done.
Amazing.
Yes. It's unbelievable when you finish it. It's a real sense of accomplishment. It's well worth it. So just out of for information, I'm looking at getting a laser paint stripper. This is something new that the airlines are now using. They use a laser to strip off the paint, which saves a tremendous amount of time. So, what's that?
It's like cook it off.
Yeah, it literally cooks it off. That's exactly how to word it. It heats up the paint, and because it heats it up so fast, it literally pops off the surface. And that's what they're doing with airliners now. They use the laser thing. It doesn't hurt the metal behind it, as long as you don't hold the laser right on it. But when you run it over, it's like a little circular line or whatever. It heats up the paint really fast, and because it changes in temperature so quick compared to the surface, it literally springs off there because there's you've got the contraction, expansion, things like that, when that happens, it really pops off there. So, and I'll let you know how that goes, because if we do the 150 right now, I got a super deal on the 150, and that's because it looks horrible. And you look at it and you'd say, oh my, there's no way I'm flying in that. But that's probably one of the safest planes over there right now, because it's just, all it needed was some engine work and stuff like that. And it went through as a matter of fact, I had a guy call me after I bought it. And he said, I'll give you twice the price that I paid for it. That's how he saw the value in it, and he didn't care about the paint or anything like that. So I really, if you're not afraid to do a little work, you could actually get a really nice aircraft. But we could talk about that later on. Yeah.
So what do the questions look like for weather on the written test?
So you're going to get some of these questions. It's going to talk about pressures. You're going to get a ton of questions about atmospheric pressure. You're going to need to understand how the barometer works. Why we use the barometer itself. But the big thing there is, if you have a good understanding of, what pressure is, and what altitude is and how they relate to each other, you're going to have a much better chance of answering questions correctly. It's, again, if you have that, you're not uncertain of it, I definitely would go over it. And it is tough. Like I said, a lot of pilots would not be able to answer a lot of these questions, just even basic ones, like does pressure decrease when altitude increases? Yes, it does, right? Pressure decreases as you get higher. So that's a pretty basic one. You guys know it. But again, if you ask some pilots that's been around for a while, they may not be able to answer it.
How much does that laser paint stripper cost?
It's probably around anywhere from you could spend tens of thousands of dollars on something, but probably around $3,000 to $4,000.
So it would save you tens of thousands of dollars in the long run.
Yeah, because I'd use it for more than that. It's actually used for stripping off most of that. So let's talk a little bit. We're actually going to get into this part of it later on. These are some weather symbols right here. I just want to put them up here just to get you guys ready for the next section right here. So these denote different types of weather or winds conditions here. So calm wind is just basically a circle. There's no wind barbs on it or anything like that. This right here is telling us the wind is coming out of this direction right here, and it is at 5 knots. It's a shorter little nub there. That's that little nub right there. It indicates. So it's, in this case, I would say that the wind is out of the northwest at 5 knots is what we'd say. Oh yeah, they got it right up here. Northwest, yeah. And then this right here, again, the wind is coming out of this direction right here. And this is our station. This could be Reedsburg, it could be Baraboo, but you'll see these symbols on a map. As a matter of fact, let's kind of switch over to here and show you. That. Yeah, this one gives you an idea of what it's like. So here we have some wind barbs. These are again just showing, this is one type of symbol that they use. It doesn't have a little dot right here, but you can see these little wind barbs right here. These are called barbs, these two little lines right here. Here's the wind direction, and then the barbs are always going to be at the end of the arrow. It's like a little arrow. It's showing you that it's coming out of this here. So a full barb is like here. These are two full barbs right here. Can you see this right here? There's two full barbs, those are 10 knots. Okay, whenever you see a barb, it indicates 10 knots. And then the half a barb is going to be 5 knots. So what would that be? 25 knots. Yeah. So at this altitude, it's going to be 25 knots out of the west, it looks like. Now you're going to see some also find one in here. Really close to some of them here. So there is another type. When you go over 50, they don't want to keep putting those little bars on there.
Yeah.
Yeah, right here. Oh, there was. Did you see one?
Yeah,
There
I
was.
saw
Oh,
one.
okay, cool.
That's,
That's that.
there's actually.
Oh yeah, there we go. Okay, all right. So good example here. So this, see how it looks like a flag instead of a barb? That indicates 50 knots. So that makes sense. You're not going to have a huge change in winds in such a close proximity there. So this is showing 50 knots. This is showing what right here? 45 knots. Yeah. And it's, what direction is it?
South.
It's pointing north. Yep. So the wind is coming out of the south, but it's going toward the north. So if I'm flying up here, if I'm flying, let's say down south right here, I'm gonna have a huge headwind right there. But if I'm going north, I'm gonna have a great tailwind. I'm gonna get up there really fast. Okay, does that make sense? Right. So those are the types of symbology that you're going to see in like weather maps. That's pretty standard. Sometimes the circles will have different meanings there. We'll get into that in a second here. One other thing I wanted to talk about too was on your maps, you also have, you can also discern quite a bit about the pressure system based on how close those isobars. So here's our altimeter setting right here. Again, this is in millibars, it's not in inches of mercury. But the closer these isobars are, the steeper the gradient. Okay, so in this case, this is going down. Okay, so what is this, a high on this side or a low on this side? It's a high pressure, yeah. Definitely compared to this, you get relatively high pressure 1028 here, and then low pressure 1008 here on the low side. So if you had a bunch of these contours here, that would tell me that it's a real steep face. Have you ever seen like a map? You looked at a map and they've got contour lines on it, and you know the area. So if you go look at a contour map of, let's say, Devil's Lake, if you look at that, there's going to be some very steep gradients going down to the water there, because the bluffs just drop off all of a sudden, like, was it like 200-300 feet where it drops down. So you're going to have a steep gradient. That's exactly what's happening here. It's showing, you know, if you see those isobars really close together, it's going to be really steep. Did you have something right there? So again, closer they are, the steeper the gradient. Now, the other thing to keep in mind about that, when you have isobars really close together like that, you're going to have stronger winds. You know, just like if I was going to walk from the top of Devil's Lake down, I would choose to take the longer route that has the spread out isobars, or those contour lines. But if I want to go down really fast, I could just jump off the edge of the cliff and go straight down. So it's really steep, right? That's what you have to think about when you're flying. If you have those steep gradients like that, where they're really close together, you're going to have lots of wind. There's just no getting around it. It's whether it's high pressure, low pressure. It's like, you know, it's the same as in terrain. It's going to be a rough line. Okay. Let's see here. And okay, so this is a very important concept right here. And I think we've already talked about it, but I want to, you know, go through this again just to make sure that you guys get this. So this is talking about, and I'm not sure if they even have this. Oh yeah, they do. This is on 1214. So this is talking about capacity of air, a parcel of air to hold water. So here we've got, let's see, 9 gallons of water here per cubic meter of air at 10 degrees Celsius. What this is telling us is we can actually, as the air gets warmer, its capacity to hold water is greater. Okay, and when you think about it, it kind of makes sense you know, when you have hot air, the air molecules are spread out further, right? As opposed to cold air, air is more condensed, right? So I got in my right hand, I've got a parcel of air that's really frigid cold, and then on my left hand, I've got a parcel of air the same size that is really hot. So the one on the one on my right hand can't hold as much water as the one in my left hand, the warm parcel of air. And that's because, again, the warm air, the molecules in it are expanded. There's more room for H2O particles or water particles to be in there. So you have more capacity to store water on there. And here you can see, and that's what this is saying right here. This can hold 9 gallons at 10 degrees Celsius, but this parcel of air can hold 17 gallons at 20 degrees Celsius. And if you go up to really hot, this is getting close to 90 or maybe around 90 right there, we can hold 30 gallons of H2O in that same parcel of air. So, so that's really important. We need to understand that. So, and then here, if the temperature is lowered to 10 degrees Celsius, the air can only hold 9 gallons of water, 8 gallons. Okay, so what they're describing here is water condensing. At some point, if I take my parcel of really hot air that's got lots of water in it, and I mix it up with my cold air, let's say, because the colder air doesn't have the capacity to hold that water, what do you think is going to happen to it?
Those droplets of fluid too.
Yeah, you get droplets of rain or water vapor, visible water vapor. That's where clouds form. You remember before I was telling you, I was going to show you how to calculate the altitude to get to smooth air. Okay, well, this is what we're going to use. We're going to use this method right here. Okay, so keep that in mind. So if you've got really warm, let's just take a parcel of warm air. Let's chill it down. Let's say we've got 100% humidity in there. That means that it's maxed out. It can't take on any more moisture. And then we lower the temperature of that parcel of air. What's going to happen is the water is going to produce visible moisture. You're going to actually see clouds. You're actually going to get rain because the parcel air can't hold that. It's getting colder, right? Cold air can't hold as much moisture, so it's got to do something. It creates water vapor, visible water vapor, and then ultimately it says, I can't hold any more, and it just starts spraying out rain. So it drops out from it. So that's where we get precipitation. Okay, when you've got a warm, humid air mass getting cooled down, when it cools down, it produces clouds like this, and it again produces precipitation and things like that. So this is a super important concept to understand. Okay, I can't stress it enough because this you'll definitely get questions about this. That whole process, that's called relative humidity. Okay, so when they say relative, because it's relative to temperature. So what they mean by that is, a super hot temperature relative to a cold temperature parcel of air can hold much more water than a colder parcel. Okay, so 100% parcel or 100% humidity in a warm parcel of air is going to be able to handle a lot more water, right, than a cold parcel. That's where we get the relative. It's relative to the temperature. So we got a cold parcel, again, I won't be able to hold it nearly as much water. At some point, the water is going to condense and it's going to create dew, rain, whatever, clouds, whatever. So when we start getting around the dew point, that's what it's called, the dew point, where water turns into water vapor. Like right now, if I go outside, you may not realize it, but the air does contain water in it. Even the water in this room, there's water vapor in this room. Now, if we chilled this room down really fast to like 0, it would get foggy in here. Okay, and that's when we start seeing fog in here. Let's say in this room, let's say we chilled it down really quick. We started seeing fog in here. That's the dew point. That's when the air has basically reached what we call saturation or 100% relative humidity. And then you go below that temperature, and then it starts to condense into rain and stuff like that. super important. I can't stress this enough. Just understanding this concept of relative humidity. Again, relative to the temperature that you're at. Okay. So again, we know that cold air can't hold as much moisture. So when hot, warm air meets cold air, it produces weather. And that's what we see. We had that huge snowstorm. Every time we have a snowstorm, if you guys want to go online and look at what's going on with the weather, here's what you're going to see. I can almost guarantee you 100%. You're going to see warm, relatively warm air that's somewhat humid coming up from the Gulf, and you're going to see a polar air mass coming down from the north. And that's where we get these massive snowstorms. And that's also where we get some pretty good thunderstorms. When you have those two air masses colliding, you've got the polar continental mass, the polar coming up from the North Pole, and continental meaning it's over the Earth. It's really cool. It hits that moist tropical air, and then it produces moisture in the air, and then those thunderstorms. But again, look at that. Whenever you see a major, like a thunderstorm or something like that, or snowstorm, just go online and look at the weather charts, and you'll see what I'm talking about. You can almost guarantee you can predict when we're going to have major weather events just based on that one simple thing on there. So okay, does everybody understand that? I realize I'm throwing a ton of stuff at you. Yeah, I know it's not super simple, but the big thing there is just understanding that hot air has a capability of holding a lot more water, and cold air has less capability. And when you mix the two, if the air cools down, at some point, you're gonna the water in that parcel has to be expelled somehow. And it's usually it starts with visible water vapor like clouds, or rain or snow or something like that, or dew on the ground. So, okay.
So dew point is 100% humidity.
Yeah.
That's okay.
Yeah. When the temperature, so there's two measurements there. There's the temperature, the ambient temperature around us right here, and then the dew point is just a number that is telling you the temperature at which, if you chill that water down, you're going to get visible moisture. That's the thing there. And again, that's a super important concept to remember. So, and every airport has it. They'll have a weather reporting station. They'll always give you the temperature and the dew point. And what they're telling you is if the air were to chill down to the dew point temperature, then you're going to get visible moisture or fog or clouds or something like that, or rain or whatever. If you look at airports that have rain right now, if we were to go to airports that have rain, temperature and dew point would be the same. Okay. Yep.
Is that why it's like foggy on like cold mornings after like a summer one day?
Yeah. Absolutely. You'll see that again. That has to do with the air cooling out at night. You get this terrestrial radiation or whatever. I think we talked about it a little bit anyway. But the air cools down, and it because there's still moisture in the warm air, it produces fog or dew, which we see a lot, or frost. That's another product of temperature dew point, especially when it gets really cold. So we see the effects of it more in the summertime than we do in the wintertime. When you have a tropical air mass that's got lots of water in it, moving up north and polar air mass hitting, then we get those huge huge snowstorms. We did this last time. And that's exactly what happened. If you look at the turns, you can see this. Okay, everybody understand? Right. And again, I would probably read through this again to make sure that you get it, because this is a very important thing. This is what drives a lot of our weather. This is what produces a lot of our bad weather. When you have those temperature dew point spreads when we get really close. There's a lot of things we can do as pilots before we take off to verify that that the weather is going to stay all right, even though it looks really nice out. Maybe the temperature dew point here is really close, so it could, if there's some instability, maybe the temperature dew point are going to get really close, and all of a sudden the airport's just going to get socked in. So there's more to it than that, but at least you have an understanding of that. My guess is the temperature dew point today is they're probably at least 6 to 7 degrees apart from each other, just by looking at the clouds. I can tell you that. And as a matter of fact, I can prove it. Let's just test this out so you can see what I'm getting at here. Let's see. Let's go. It is a little warm. It is. Yeah. We saw definitely some humidity here. So let's go back to our home here. as I should have. Okay, so we'll look at variable here. So this is what we're getting into in the next chapter. So we'll talk about this a little bit more. So you've got KDLL, that's the ICAO identifier for the variable right there. And this right here, it tells us the date. This is a what's called a BTAR right here. This right here is the date section. Here's the time section. Like, we're going to get into this in a second here. So, but one of the elements that they talk about here is this right here. Remember I said 6 to 7 degrees. So the temperature is 22 degrees Celsius, and 14 degrees is the dew point. So 7 degrees difference. So that's again, by looking at the clouds, I'm estimating they're probably around, well, here they're saying they're 3,500 feet. And that's, I was thinking about 3,000, but that's, they're scattered. These are what we call scattered clouds. That's what that SCT right there stands for right there. And this is Baraboo just 9 miles away. So this is what Baraboo's reporting right now on there. And then there's actually several layers of cloud there. So, and again, we get into these weather reports. This is what's called an observation report, or a METAR is the actual title. Right. Right. So here we go. Yeah, here I just was explaining this. Cool polar air, warm air rises unstable. You've got warm surface. The cool air hits that warm surface, it rises, and it creates some unstable air, and that's where we get our little thunderstorms. Things like that. Here's a good example of just fog being produced, in a valley. Lots of shade down here, so it's really cool in this valley right here. Yep.
So why is it called radiation fog?
Is that radiation fog is, as opposed to convection or advection fog, it is basically static. It's just something that's just gently radiating from the surface of the ground. That's, think of radiation as that type of it. There's not like a lot of wind currents. As a matter of fact, radiation fog, there's really no wind at all. It just kind of radiates from the surface. From the air is, got warm air on top and cool ground on the bottom, relatively cool. And so the temperature dew point gets really close and it condenses and produces this radiation fog. So not a lot of wind, but it just produces the radiation. Does that answer?
How does fog disperse? Like, how does it?
The fastest way for fog to disperse usually is just a gentle breeze. It doesn't have to be much. You can have like a 5-knot wind, it'll dissipate. Now, that's assuming that conditions improve as far as the temperature dew point. If the temperature dew point stays together and there's still sufficient water vapor in the water in the atmosphere, you'll still get fog. It's just going to be moving. But like during the day, usually we get fog in the morning, and then it usually clears off later in the day. And that's because if we're here, this is the Earth right here, and here's the sun. In the morning, right here, the sun's over here. It's hitting it like this. The ground is relatively cool, but as soon as the sun rises, it hits that ground, warms it up, increases the temperature. The dew point still stays the same, but the temperature increases. And because of that, the temperature dew point increases. And so now the fog starts lifting into clouds and things like that. And again, it depends on, how cold it is. If it's on a cold winter day, you can still have fog, but it may be that, again, there's not much moisture in the air, and so it just dissipates instantly. So, okay. So we understand that concept of temperature dew point. So again, temperature is the temperature of the parcel air, can be variable, wherever. And then the dew point is the point at which water vapor actually forms in the air if we were to cool that down. So you're typically going to see a temperature dew point of like 22 or whatever, and then slash, and then it'll have the dew point, which is going to be colder than the air. So it's always going to be a lower number for the dew point. So that's what you have to chill that air down to produce some moisture. Now, you're probably wondering, well, how did I figure out what the clouds were? How can you figure out what the height of the clouds are based on temperature dew point? So this is the way to do it. So we know that the lapse rate of temperature, you know, as in a standard atmosphere, if we go up 1,000 feet, the difference in temperature is, does anybody know what it might be in Celsius? Roughly, it's about 2 degrees, okay, per 1,000 feet. If we were just in a standard day, in standard conditions, right? We go from sea level, we go up to 1,000 feet. The temperature difference is going to be cooler, right? Because as we rise in the air, the temperature gets cooler. So it's about 2 degrees cooler at 1,000 feet, 4 degrees cooler at, you know, at 2,000 feet. Yes, thank you. But based on that, I know what the temperature difference is between those altitudes then, and I can kind of guesstimate where where the temperature and the dew point are going to kind of collide there. And there's another part to that I think they talk about here. Let's see. Yeah, actually they do on page. I would definitely read through this, but let's see. Yeah, here we go. So this is on page 12-14. So, and it's on the left-hand side. As moist, unstable air rises, clouds often form in the altitude where the temperature and dew point reach the same value. Okay. When lifted, unsaturated air cools at a rate of 5.4 degrees Fahrenheit per 1,000 feet, which is roughly.
So that would be the 2 degrees Celsius.
Yeah, it actually is it's a little bit different than 2 degrees Celsius. It's close to it. That's actually closer to like 3 degrees Celsius there. So, and there's other reasons for it being a little different than the standard lapse rate for temperature there. Let's see. So, let's see. Yeah, and because the air is unsaturated, I guess that has something to do with that 5.4 degrees. But yeah, per 1,000 feet, the air cools at a rate of like 5.4 degrees per 1,000 feet. And the dew point temperature decreases at a rate of 1 degrees Fahrenheit per 1,000 feet. So that leaves us with basically 4.4 degrees Fahrenheit per 1,000 feet. So that means that, you know, if the temperature is, let's say it's 20 degrees on the surface, and the dew point is, let's say it's 10 degrees Fahrenheit. That is, so 20 degrees Fahrenheit and 10 degrees for the dew points, and 20 and 10. Then roughly, you're going to start seeing clouds form probably around like 2,000 feet above the ground. Is where you see it there. So I could read through that a little bit. If you guys have questions on it, we can go over it. I don't want to spend a lot of time on it, but they've got formulas here where you can calculate it. If you can understand that concept, that as you chill air, it produces, it can generate, if it gets to that dew point. If you chill a parcel of air to the dew point, it produces, you know, visible moisture. That's a good step forward in understanding that. So. Okay, let's see here. Dew and frost, again, that's all part of the dew point forming. Fog, again, you guys understand that happens when when you get visible moisture from the temperature chilling down to the dew point there. Okay, so let's talk about some clouds here. Let's see here. So these are the different types of clouds here. We've got four different types of clouds. You've got low-level clouds, middle clouds, and then you have high altitude clouds right here, high clouds. So the ones you're going to see down here close to the planet, this again usually are less than 6,000 feet. You've got stratus clouds. Those are the nice smooth clouds. If they don't, there's not a lot of features to them. Whereas cumulus clouds are going to be a little bit puffier. Nimbostratus clouds, that's going to be producing lots of rain. They usually have nimbostratus clouds. Nimbo, by the way, that prefix means rain. And stratus means stratified. You've heard of like stratified rock. You know, it's straight, you know, it's like the layers of stratified stratus or whatever. So it's very smooth. Whereas cumulus is going to be like bubbly like this. This is kind of like a bubbly cumulus cloud here. So, and this is a nimbostratus because it's got a stratification layer right here. But these right here are going to be cumulus clouds there. You can see because we've got little puffy designs here. You can see the altos cumulus. Alto means middle. That's same thing as in music, I guess. Alto, they're middle clouds there. So I notice how these are puffier. You know, they've been a little puffier. And then alto stratus again, very smooth stratification of the clouds there. Yeah. So yeah.
So stratus for like your clouds when there's like a complete overcast beach.
Well, you could have a complete overcast with cumulus clouds. So what you're looking at, so if I look outside, can you guys see outside there? Those are cumulus clouds. They're about 3,500 feet. And they're shredded. Some of them are shredded. Some of them are pretty well formed. You could get and learn a lot by just looking at a cloud. So if the bases of a cloud are really dark compared to the surroundings, that means there's a lot of probably moisture inside there. There's a lot of water vapor. And that means that could be a good candidate to produce some rain. So those don't look all that bad, but when it starts raining, just take a look at some of the clouds and see the differences in the lightness through them. So if it's really dark around and it's producing rain, okay, well that's because there's a lot of water vapor there. So the cloud is really high, sunlight can't get through it, and it's
We have some dark ones over here.
Yeah.
Yeah, you can see on the bottom.
Yeah, you can see those right there. And they may or may not produce much rain at all, maybe a sprinkle or two. When they start getting really high, that's when you get that vertical development. That's when you get the potential for producing a lot more rain and stuff like that. So it might, we'll see what happens. I know we're supposed to get some rain here sometime today, but those are all classified as cumulus. That would be what's called a scattered layer of cumulus clouds, or scattered layer of clouds, because there's so much blue. You can see there's a lot of blue sky in there. We could still fly on a VFR day. We'd fly up above the clouds there and still be in VFR conditions without having to file an IFR flight plan. So again, cumulus clouds. So stratiform clouds, they can be a little wavy, but they generally don't have those cotton candy-like outlines. They're just basically very smooth there. Okay, so 3 different types there: stratus, stratocumulus, and really there's in the lower areas here there's cumulus clouds. Really, when we talk about stratus and cumulus, those are the 2 types of clouds you're typically going to see. But they add these prefixes onto them to identify what part of the atmosphere they're in. So just the straight stratus clouds, cumulus clouds, they're all, if they don't have a prefix like alto, that means that they're low to the ground, okay, like within 6,000 feet. Alto means they're middle, above 6,000 to 20,000 feet. And then cirro means like super high. That's going to be like over 20,000 feet. We're obviously, as private pilots, we're not going to be worried about flying unless we're flying commercial jets. Then we're going to be a little more concerned. But the thing is, when you get to this altitude, what happens to the temperature? So the temperature drops. It drops really fast. Okay, so you're down. You're probably at what is it? Maybe like 60, 70 degrees below zero at this altitude right here. When you start getting up to these like 40,000 feet, it's really cold up there. What do we know about cold air? Can it hold much water vapor? No, it can't. So there's not much water vapor up here. It looks like it when we look at the clouds. We see those clouds up there, but because the air is so cold, there's not as much water vapor. You could still run into some ice though, but it's not going to be nearly as bad as ice, for instance, down here. If I'm down below the ground within 6,000 feet and I start loading up with ice, I'm going to be really concerned. As opposed to running into ice. And I've run into ice at over 20,000 feet, and it's just basically what we call lime ice, which is like a milky air. I think it's got like a lot of air bubbles in it, and it doesn't hurt the aircraft. Down here, however, you can build up clear ice, what's called clear ice, and it is bad really fast because again, the atmosphere is warmer down below. It has the capability of holding a lot more moisture, and because of that, when you're flying in there, you could get a lot of ice. Anyway, so regular low clouds, alto clouds, and cirro clouds, regular cirrus clouds. And again, they could be either stratus or cumulus. Stratus, smooth, cumulus, puffy. Think of candy. And then the fourth type is clouds with like extensive vertical development. So and we're talking about thunderstorms here. So in this case, you've got a towering cumulus, and that's basically like a cumulus cloud right here, but it's towering. And again, if we do have thunderstorms later today, if we're fortunate enough to see them coming, you look at them, look for that anvil if you can see it. It's always pointing in the direction that the storm is moving. So in this case, if we have a storm system moving over here, it's going to look like this. We're going to look up in the sky right now and saw a thunderstorm coming. It would have the anvil here, and then this big pillar of moisture of cloud there. Yep.
So when you see it, so when you see an anvils going off to the right, and when you don't, it's going to
yeah, you can get an idea. Yeah, if you look at it, there's always that shelf at the top, though. If it's a really strongly developed thunderstorm, sometimes it kind of poops out and it doesn't produce much. It may not develop that anvil, but if it's strong enough, what's happening is it's hitting that there is a thermal change, where the air is really cool up here. It hits that, and then it just stops developing. It just freezes right there, and then whatever the winds are up there, they're going to be pushing it in that direction. So that's why you get that anvil there. And that's where you get right here on this side of a thunderstorm. This is where you're going to get the hail and stuff like that. So as a thunderstorm moves over, you've got your let's say pillar of cloud right here. As it moves over, you got the big anvil right here. So the wind is pushing the storm this way, right? Okay, and when it does that, it's pushing whatever is in that storm, moisture, hail, and things like that. It's always going to spit out from here. So if I'm on this side of the thunderstorm, and as that storm moves this way, I would expect hail on this side, if there is going to be hail. You won't see it on the backside. Generally speaking, you're not going to see it because the wind is pushing this whole thunderstorm in this direction. It's actually causing that hail to spit out from the top of it. And that's why hail, it's probably one of the most scary things if you've ever been in a hailstorm. It's really terrifying. In a plane, and to be bad enough where it actually damages the aircraft. I've seen planes that have been peppered by hail. People survived it obviously, but they can damage the aircraft.
So is it pretty obvious when planes flew through hail before? Or?
Oh yeah. It looks like a golf ball. Seriously, yeah. You look at it, and if it was bad enough, if it was really severe, it would have broken the windshield on it, or maybe other ones, the lenses and stuff like that. It doesn't happen very often, but planes that have been through hail, even small hail, when they hit the plane, it just dents that. You'll see it on the leading edges of the wings. If you look really carefully on the leading edge, you'll see like little pits and things like that. Sometimes it chips off paint and things like that. So yeah.
So how much does that affect aerodynamics?
Not bad. It won't affect it all that much. So obviously, it probably affect the pilot's ability to fly the plane because it's loud. If you've been in rain, just rain itself is really loud. Like small aircraft, heavy rain is. Okay. Okay. So remember we were talking about air masses. So the descriptions for air masses. So there's this right here is I'm not sure. Yeah, figure 23. These describe some of the different types of air masses. So the M stands for maritime. Maritime meaning water, right? Maritime, we think of like, oceans and things like that. The C stands for continental, okay? And then so that just describes, where it came from, either, a continental mass or a maritime mass. So water as opposed to land. So you've got your continental polar. The P stands for polar. So there's continental polar air mass that moves in. You hear about this a lot. If you listen to newscasters, they'll talk about we've got a continental, polar continental air mass moving in. It's going to produce some really cold temperatures. So that's what you're seeing right there. So and also the EOS will use Arctic mass to produce basically do the same thing. Yeah, A is just Arctic, yeah, and it's just another way of saying continental polar. They're basically the same thing. So in maritime, MP stands for maritime polar. So that's obviously on the East Coast. That's where they get their nor'easters. You've heard that term before, I'm sure. They get some pretty nasty weather from that. Maritime T, the T stands for tropical. So you've got really two different types of air masses: maritime air masses and continental air masses. Continental are over land, maritime are over water. Okay, that's all you have to know about those. And then you have where they came from, the tropics or the polar regions. And then you can mix the two. You get continental polar, tropical polar, not tropical polar, I'm sorry, maritime polar. And then you can have, again, a continental tropical or maritime tropical. So continental tropical is coming up from Mexico. That's why you see the air mass flows over Mexico, and it's called a continental tropical because it's coming from the tropics moving up here. Now, the thing you need to know about air masses, and this is what will be done today, is the air masses are modified by what they travel over. Okay, that's why that's why we label them maritime tropical. To me, a maritime tropical air mass. Well, actually, let's ask you a question on this. So, a maritime tropical forecast air mass, is that going to have more water in it, more likely than a continental tropical?
Yes.
Yeah, absolutely, because it's sucking up all that moisture from the Gulf, from the maritime.
So is it going to be slower? Since
What's that?
Like, is the maritime tropical going to be slower because it has to push like water too?
That's a good question. I don't know. I honestly don't know. I think they would move the same. It probably depends on how the pressure gradient is. If you've got a really strong low pressure system, that's probably going to dictate how fast it moves. So if it's a really strong tropical low that moves over here, you're going to have that huge gradient there, and that might affect how fast it moves in there. And then how weak this area is up here. If you have a really weak low up here, it could draw that weather system into it a little bit quicker. Okay. I think, yeah, we'll go over a little bit more on air masses next week when we talk about some of the symbols and stuff like that. And then we'll dive right into the aviation weather services and we'll go through that. So any questions at all? All right. And then if you guys can, please keep going through those quizzes if you can. And take them if you can, just for helpful. And the other thing too with the Sporties, is anybody starting to use the Sporties questions? Is it? Yep. Yeah, Sporties is awesome. They've got some really good material in there. They cover a lot of the stuff that we cover here, so just a good refresher there. So.
Yeah, someone up there.
Oh, that's pretty good.
If you want.
Yeah, it's everyone.